All right, so thanks very much for the invitation to Birmingham. It's my first time in Birmingham. It's actually a really beautiful campus and actually sunshine. So I'll talk about 5D SCFTs and canonical singularities, and you might have read the abstract, and now you have a chance of leaving, because while preparing the talk, I realized that I would actually focus on the symmetries of these theories rather than what I said in the abstract, magnetic quivers and the Higgs branch, because somehow there's much more to be said new in the symmetries than in the Higgs branch. So, but it ties in well with the other talks today by both Matt and Matt. Okay, so let's get started. 5D SCFTs or superconformal field theories. Well, you could say it's sort of a physical prediction of string theory that there are these conformally invariant supersymmetric field theories in 5 dimensions and 6 dimensions. So this is something that if you are a perturbative quantum field theorist, you would not think that that should actually be a thing, because these theories, essentially, these kind of fixed points, they live at infinite coupling. And if you just look at sort of the low energy physics in the IR, these are actually free theories. But string theory tells you actually there should be such fixed points. And up to some very, very sort of, small corners that you can study using other methods like the bootstrap, with the superconformal bootstrap. Really, string theory is sort of the only way of getting information about such theories. And actually, in the past couple of years, we've seen a lot of, well, you could call it resurgence in the interest and actually progress understanding these theories. And that has to do with a couple of factors. But the main sort of thing, how it ties into the M cubed story, is that, well, M theory is a crucial factor here. And then it sort of is compactified on a Calabi-Yau threefold. It's a singular Calabi-Yau threefold. These are canonical singularities. And if I take this 11-dimensional theory, put it on the 6-dimensional space, then I get a 5-dimensional conformal field theory, if this is a canonical singularity. And here, the Calabi-Yaus I'm thinking about, they're actually non-compact. So I'm not interested in compact Calabi-Yaus, they're just local Calabi-Yaus. And so in physics terms, this means we're decoupling gravity, we're just looking at the field theory. So what is a canonical singularity? Well, it's a singularity, so these are threefold, complex threefolds. We can find a resolution so that the canonical class is just basically the canonical class of the original space plus a sum over exceptional divisors from the resolution process, where these AIs are positive. And in fact, if the AIs are all positive or equal to 0, and if they're actually equal to 0, then that's sort of a nice, smooth Calabi-Yau resolution if you started with a trivial canonical class from the beginning. If some of these are non-zero, then after you do the resolutions, you're still left with some remnant terminal singularities. And all of this has very intricate physical implications. But sort of the key is M theory provides a dictionary between these geometries and some 5D physics. And that's what we'll be discussing. Okay, so we'll ask basically 3 questions, but we'll be focusing on the last one. So M theory, or this M theory 5D correspondence, you want to call it that, you could ask these field theories have moduli spaces, parameter spaces, so vacuum spaces. So you could ask there's something called a Coulomb branch. So if you're familiar with 4-dimensional n equals 2 theories, the structure of the moduli spaces is not dissimilar. And these are all theories with 8 supercharges. So these 5-dimensional n equals to 1 supersymmetric theories have a Coulomb branch. What is a Coulomb branch in terms of the geometry? They have a Higgs branch. What is that in terms of the geometry? And then actually, how are symmetries of 5D theories encoded in the geometry? So in the last talk, you heard a lot about interesting topological operators and 3-dimensional theories. So what we'll be asking here is what kind of topological operators and what kind of properties do these have in these 5D theories? But since we're realizing the 5D theories and M theory on these canonical singularities, we actually need to understand how they're encoded in the geometry. So that's sort of the storyline. Okay, there are lots of papers on this. And so now I'm going to basically do this confession that we'll be really focusing on these generalized symmetries. So generalized symmetries are going to be things like what Matt talked about in 3 dimensions, but much more generally, nowadays physicists think of symmetries as topological operators in your theory. Right, so in this case of these 3D theories, these were topological lines, and you were looking at what kind of fusions do they obey. In a similar way, in a 5-dimensional theory, you could ask, what are the topological operators, and what kind of fusions do they obey? And so these are global symmetries. I'll be only discussing these kind of global symmetries. So if you're thinking about sort of codimension 1 topological operators, then essentially you sort of have, say, in 5 dimensions, a codimension 1 operator that could enclose a point-like operator. So in fact, these codimension 1 guys, their topological operator is simply what generates 0 form symmetries, or just global standard flavor symmetries. So that's sort of what we learned from Noether. But once you actually just say any topological operator will correspond to a symmetry, then you could say, what about codimension 2 or codimension p plus 1 more generally? And we'll just say those actually generate the p-form symmetry of that theory. So in 3 dimensions here, these line operators were codimension 2. So these were generating a 1-form symmetry. In the same way here, the codimension 2 guys in 5 dimensions, they will also generate a 1-form symmetry, but more generally, you have now, because you have more dimensions, you have also more complicated symmetry structures. And we're not just interested in the types of symmetries that we have, but also how they actually interact. So let's look at this a little bit more sort of, still schematic, but perhaps this is helpful. So if you just think in terms of standard quantum field theory, stick to 4 dimensions, then you can think of a point-like operator. You surround it with a sphere, you measure the charge by basically collapsing this topological sphere, and then that gives you the charge under that symmetry. And in that way, you can think of this codimension 1 topological operator as sort of generating the symmetry. And what I've drawn here is just saying you could have now p-dimensional charged object and surround it with a suitable dimension that links in this space-time dimension that's codimension p plus 1, green ball. It doesn't have to be a ball, it could be a topological object. And now you collapse it and that computes the charge. And that's basically these kind of objects, omega g. Here they will actually be the generators of the p-form symmetry. Okay, so that's this. Now, if these things can actually, so for example, for p equals to 1, we said these are line operators. And then, for example, in the pure gauge theory, this would just be sort of the center symmetries in 4 dimensions. Now, sometimes these extended operators, they can end. The line operators can end on local operators. And that can mean that, for example, now you can take this topological operator, it linked before when the line couldn't end with this line operator, but now actually you can sort of strip it off and collapse it to actually get now a trivial charge. So if you have line operators that can end, these local operators basically they can what's called screen these 1-form symmetry charges. So here this charge is trivial for this line operator. Okay, so the story is basically just starting with these p-form symmetries, because once you have a theory with 0, 1, 2, and so on symmetries, you could ask, when I actually look at the structure on these p-form symmetries, do they just form product structures, or they actually could form something more complicated, what's called a higher group? And also, in fact, are they actually forming groups? So in every p dimension, so any p-form symmetry, does it have to satisfy a group type fusion, or something more general, like in these things that we talked about in 3 dimensions, where they're actually non-invertible. So they have some kind of structure, the sum over these ni that Matt had in his talk. So these are all kind of questions that we'd like to answer. And now you'll ask, why is this important in 5-dimensional superconformal field theories? Well, it's important because, first of all, these are, as I said, strongly coupled theories. So you can't just do Feynman diagrams and sort of calculate and get better information about these. what you would like to have is some kind of robust information. And global symmetries is sort of one of these gadgets that actually are robust under RG flows. For example, the global symmetries can have Toft anomalies. So those are RG invariant. So if you calculate them somewhere where you have some computational control, you can take them also to the strong coupling. And what we'd like to actually do is incorporate these symmetries. More generally, I wrote this word down here, this categorical symmetry, but it's really just a super set of all these things. These generalized symmetries in this geometric realizations of 5D SCFTs. So that's basically what we'll be doing today. So the plan is give you sort of, I'm sure not everyone here is familiar with 5D SCFTs. What is the basic dictionary? Then talk about the Coulomb branch, that's the resolution part of the story, how the symmetries are implemented there, and then the plan of the Higgs branch, but actually do more symmetries. Okay, are there any questions so far? We'll basically maybe just start and then we keep you keep asking questions because I don't know what the background of the audience overall is. So a 5D CFT we said is basically an M theory compactified on a canonical threefold singularity times Minkowski space. So the 5D theory lives on the Minkowski space, and the singularity can be isolated or not. In fact, for many of these symmetry considerations, you don't want it to be isolated. And it'll admit a resolution. We discussed this, right? Sometimes this resolution will have some remnant terminal singularities. And so basically the dictionary is these canonical singularities, the singular locus, right? And say the scalar moduli space, that describes the superconformal field theory. And then actually going out into the Kähler cones, you have these kind of resolutions, you can blow up the singularity. That actually models what's called the Coulomb branch. So these are modeled by, in the physics terminology, vacuum expectation models of scalars and the vector multiply. Then sometimes these singularities, right, you also admit deformations, and those deformations will model the Higgs branch. So those are vacuum expectation models of the hypermultiplets and scalars. And we'll be essentially focusing on the Coulomb branch most of the time. So one of the key points is that although we're studying the superconformal field theories, the Coulomb branch has some interesting, nice description. It's actually given in terms of what's called an effective Coulomb branch description. I mean, it's a U1 gauge theory with matter and Chern-Simons couplings. And so how do I actually obtain that description from an M theory compactification? So I consider this resolution. And for simplicity, let's actually say we have a smooth resolution, so there's a Krapin resolution of the singularity. So the gauge symmetry comes in M theory from decomposing the three-form field. So M theory has both the metric, but also three-form field. And this three-form field I can now expand along the Pontryagin dual cycles to the exceptional divisors of the blow-up. So the exceptional divisors were these SAs, and the rank of this theory is in fact determined by how many of these exceptional divisors I have in this blow-up. And each one of these, so I expand C3 along the 1-1 forms that are dual to these divisors, that will give us a U1 gauge boson and the 5-dimensional theory. And the gauge coupling is basically inversely proportional to the volume of this exceptional divisor. So here already you see, as I take the volume to 0, I go to infinite coupling. So that's exactly the picture. You go collapse it, you get a singularity. That's the superconformal field theory. Now I can also have, because it's a non-compact Halabi, I can have non-compact divisors, and they essentially, not surprisingly, will correspond to the flavor symmetries. In fact, the total number of divisors will be the flavor rank and the gauge rank. And at the end of this, on this resolved space, X tilde will have, when we reduce M theory, that we'll get this U1 to the R gauge theory with matter and Chern-Simons couplings. Like this. Now, how do I actually get a non-abelian gauge theory description? So, for example, if I have, so in M theory, we don't just have a C3 and a metric, we also have branes. We have M2 branes and M5 branes. And if I wrap M2 branes, and I can wrap them on rational curves in this resolved Calabi-Yau, if the curve is actually a -2, 0 curve, so normal bundle degrees -2, 0, those actually correspond to W bosons. This can be both inside a compact divisor, or these could be curves in a non-compact divisor, and it would be flavor W bosons. So they would give rise to non-abelian extensions of the flavor symmetry. But for the gauge symmetry, these would be -2, 0 curves in these compact surfaces. If the normal bundle degree is -1, -1, those are actually hypermultiplets. So if you actually quantize moduli space of these curves, you see these correspond to hypermultiplets. And so in fact, this collection of surfaces, if you have some non-trivial gauge description, usually will have the structure of a ruling. So you have these surfaces are ruled over some curves, and the fibers are rational curves. So think of it, for example, it could be a Hirzebro surface, and you glue Hirzebro surfaces together to get this kind of resolved Calabi. And again, the volume to 0 will correspond to the SCFT. Any questions about this? I could probably spend an hour just discussing the details of this, but this is all you need to know. And two branes on compact curves gives you basically local operators. That's the key point. Okay, so now we also have, in this non-compact Calabi, we have non-compact cycles. So you could ask, what is the physics of those? Right, so relative cycles, so X with respect to its boundary. So these non-compact Q cycles, I can wrap them with M2 branes or M5 branes. M2 branes are 3-dimensional, 5 branes are 6-dimensional objects. So you can now start wrapping these on these cycles. These are still sort of supersymmetric objects. Now, since these are non-compact, in fact, the mass of these objects, which is proportional to the inverse of the volume of these curves, is of course now infinite. So these are actually infinitely massive objects. These are defects in your theory. So if I take the simplest example of relative 2 cycles, I can wrap M2 branes. And now what I get is a particle, but it's actually an infinitely massive particle. So what these M2 branes actually, these relative M2 branes, the M2 branes wrapped on these relative 2 cycles, what they actually give rise to, they're like world lines of infinitely massive objects, particles. So these are actually line operators. So that's actually really interesting. So you get a lot of line operators in this way. Now, do I really want to consider all of these line operators? Well, we talked about this in these kind of funny pictures here. The line operators can be screened by local operators. So really, the physically relevant set of lines is not just all the lines in the theory, but the lines modulo screen. So one way of saying that is, I would like to look at the line operators, but modulo an equivalence relation. Two lines are actually equivalent if there's a local operator, O12, at a junction between two lines. So this is just a simple picture. There's one line, right? And there's a local operator that was at this junction. And in fact, if I take the set of all lines modulo this relation, this is actually the Pontryagin dual of the one form symmetry group. Right? So for most of our purposes, these are all cyclic groups, so we can just, or abelian groups, so this is the same as the one form symmetry. So this is how we get, so physically the intuition tells you these non-compact cycles are good, but we need to also mod out by this relation. And now what is that relation in terms of the geometry? Well, local operators were coming from compact 2 cycles. So, well, the non-compact 2 cycles are in H2 of X. The non-compact 2 cycles are the relative homology. Those are the line operators. So in fact, the one form symmetry or its Pontryagin dual should be calculated by this quotient of homology groups. Right? So this is basically the one form symmetry from a geometric perspective. Now, of course, to actually calculate this, you're not doing this in terms of the singular geometry necessarily, but effectively we can formulate this also in terms of just the boundary of this geometry. Right? So you could think of this as putting X tildes here, resolving the space, looking at all the 2 cycles, and then calculating this homology group. And in fact, you'll see it just depends actually on the data on the boundary. Yep. Yeah, but it's M2s on it, so there are local operators. right? They're like the hypermultiplet, they're really particles. The finite volume and the singular limit, they'll be sort of massless modes, right? So those are really the objects that you want to mod out by. Those are local operators that you can. I will actually give you a picture later on at the boundary where you can really see how the screening will actually work on the boundary, but yeah. And of course, we can generalize this, so the Q-form symmetries can come from, now there's an electric and a magnetic version, there's a 2 and 5, we don't need that, so I'll skip this, but you can easily think of generalizations. There's always going to be these p cycles, the relative ones, modulo the compact ones by which they can screen, they can end on this. Okay, so now what do you want to do with this? So these 5 SCFTs have, and that's sort of known from the 90s, also very intricate structure of zero form symmetries or standard flavor symmetries. And in fact, when you have a 5D SCFT, and the zero form symmetries I'll discuss, they're also imprinted in the geometry. If you have now a zero form symmetry and a one form symmetry, then you could ask, well, is the structure of these two a product? Do they just not interact with? They don't see each other, they don't care, or is it something more sinister? And what could that more sinister thing be? Well, this is where these two groups come in. So in fact, let's consider just a flavor symmetry group where here this non-cal F is the simply connected one. So for example, SU2. And then we have C, which is in the center of this SU2, and we mod this out. So for example, think always this math cal F could be something like SO3, and the straight F is something like SU2, right? And the C is just the Z2 center of this SU2. And if you have something like this, you have a flavor symmetry, so zero form symmetry, and a one form symmetry, then I can actually extend or refine this relation, this equivalence relation between the lines. I can actually say, well, L1 is equivalent prime to L2 if there exists a line changing operator like this, but now transformed in a representation of math cal F. So what is this object now? So let's define now the lines modulo this new relation as E hat. And this, of course, surjects onto the one form symmetry, the Pontryagin dual of the one form symmetry. Basically, right, it doesn't need to, the other guys, the gamma 1 hats, they didn't need to transform in representations of F. And in fact, right, what is inside the kernel of this is basically C hat, right? So basically, those are the local operators could actually transform in representations of this SU2, the straight F, they do not live to cal F. So what we actually get, or the Pontryagin dual of the statement is now we have a sequence, one form symmetry goes into this extension group E, goes into the center C of this flavor symmetry. This could be a subgroup of the center, but for simplicity, let's just think about this. So now if this extension sequence, right, some extension sequence of discrete groups, this is non-trivial, there'll be also a non-trivial boxed-in homomorphism acting on Hn, the C, and then gamma 1 coefficients. And why is this now important? Well, this is important because that means if there is an obstruction of lifting, these bundles for cal F, actually F bundles, so say some C for Whitney class, W2 and H2 of the F of the C, that's non-trivial, then in fact, the variation of B2, so B2 is basically the background for the one form symmetry, is now non-trivial. So this is very fast, you might not catch all the details, but you should think of B2 as, so B2 here is the background for the one form symmetry. And just like you would write A1 as a background for zero form symmetry. Right? And A1 could, for example, now have a non-trivial characteristic class. And the key point here is that the variation of this B is now dependent on this W2 class. So this sort of dependence of the one form symmetry background on the zero form symmetry is sort of the hallmark of what we call a two group. That the zero form and the one form symmetries or the backgrounds for these are non-trivially intertwined. And that may seem very exotic, but I think the lessons from the past year basically shown that these kind of two groups are really ubiquitous in Canonical field theories. And they're like almost everywhere. And we'll discuss them now in 5D. So I will geometrize this problem, and I'll explain to you how we see all this Boxian stuff from a geometric construction. But first, I actually need to talk to you about how we actually get to do concretely all these symmetry groups from the geometry. And there are two ways of doing this. One is we start with the Calabi-Yau, we resolve it, we do intersection theory, we calculate all these values for homology groups. We calculate charges of particles or of these states, and this way we can see whether there are suitable local operators that can actually do this kind of screening, can do the refined screening, and that calculates a two group. That's the first approach. The second approach is saying, well, a lot of the structure actually can be formulated in terms of the boundary of this canonical singularity. And that gives sort of a very elegant geometric way that appeared then recently in this paper here. Okay. And so what I wrote here, the SymTFT, is basically sort of a philosophical point that a lot of the structure of symmetries, the anomalies, is encoded in this boundary of the space X. Okay. So first of all, we need to talk about very briefly about flavor symmetries, zero form symmetries. And you see, this is not just about knowing the symmetry algebra, but you really would like to know the flavor symmetry group. So you need to do a slightly more refined analysis than what Seibert did in the 90s. So you really need to dig into the geometry and determine what actually is the global structure of the flavor symmetry. So the simplest class of theories is this, as I said, the rank 1 Seibert theories. These are just SU2 gauge theories on the Coulomb branch with a suitable number of flavors, which is determined or limited by requiring that actually there's a UV fixed point in 5 dimensions. So there's a peculiarity in 5 dimensions that the zero form symmetry on the Coulomb branch, right? This is so very similar to when you look at 4D theories with A2 supercharges. That's, if you have a theory like this, you should think of this as an SP1 gauge theory. The flavor symmetry is SO2NF. And you're just rotating the these flavors, and they have particular representations, and these are going to be an SO2NF flavor rotation. But there's also a U1 topological symmetry that we can construct in 5D, whose current is the star trace F with F, where F is the gauge field. Now, if you actually go to infinite coupling, this symmetry enhances. And that was sort of the first peculiarity of 5D SCFTs, that in fact, this SO2NF plus U1 enhances to ENF plus 1. So for example, the case with 7 flavors has an E8 flavor symmetry algebra. Another question is, what actually is the flavor symmetry group? And that's actually calculated by looking at which kind of local operators do we have. Is there actually something that is charged under descent of the flavor symmetry or not? And that's something that really was developed in the past years in a very full generality. And I will skip that. If you have a question about there's some nice algebraic geometry in that, but I don't want to. When do I need to stop? At past, right? Okay, good. So if you want to ask an algebraic geometry question within algebraic geometry, there's a cute story about the flavor symmetry, but I will skip this. So if you have now the flavor symmetry, now. Right, so that's encoded in the structure of the non-compact divisors and their intersection. So I said, so if you have these I think they were alpha, maybe, I don't know. So these alphas, these are non-compact divisors. So really what they are, and they're usually ruled, so they're like P1 fibered over C. There's a non-compact. And now basically the question is, what is the intersection structure of these? and what kind of curves appear in this collection of non-compact divisors. And it's important to also then see when you actually have a collection of them, are they -1 curves that, for example, are the W bosons for the flavor symmetry. So that's how you, these W bosons for the flavor symmetry, these -1 curves, they tell you about enhancement to, say, ENF from SO to M. So this is extremely, so in fact, there's sort of an invariant way of encoding that that's flop invariant and everything. Yep. Yes, people have done that, yes, for rank 1 theories. Yeah, they worked really, really hard, and then they found, I think, the E6 or something theory. Right, so these are difficult bootstrap problems, but I think for the rank 1 theories, they really found these fixed points, and they really could see that the flavor symmetry, the associated currents, I guess, for these enhanced flavor symmetry. Right? But geometrically, they encoded in the intersection theory of these compact, non-compact divisors, and what kind of curves do you have that basically correspond to the W bosons of your flavor symmetry. Yeah. So your input, I think, okay, I'm not a bootstrap person, I'm not going to answer this, but there is a paper by I think maybe Yifan Wang, and okay, I can get you the paper, and they have a bootstrap for the rank 1 theories. Sorry? You can, because you basically, the wild group would act on the roots, and to the roots you have associated these divisors. And so you can realize that too, yes. Yes, because you see the fully enhanced symmetry, right? You see not just you don't just see the cartan, you see also the curves, that these -1 curves will actually tell you what kind of, how are these states, the W bosons for the flavor symmetry charged under the cartons. So you see all of that. Why do you want to see the wild group? Yeah. I see, and that's geometric engineering in 2B. Okay, it's maybe slightly different. Yeah, right. If it's rank 1, then it's all pets, right? So maybe I should say that if I find the pen. So for these SU2 plus NF flavors, right? These have these ENF +1 flavor symmetry algebras. The surfaces are just DP or generalized. Healthier to have the generalized pet, so NF +1. And then you can see on these blow up curves, you have really -2 curves, and the intersection pattern of these -2 curves and their -1 curve, you can really see the structure of the ENF +1 coming out. Okay, any other questions? So I think that was a discussion of the flavor. Now we said we can calculate the one form symmetry. I gave you this sort of very physical picture of non-compact or the relative 2 cycles modulo the 2 cycles. Now if you actually have a resolution there, you can translate this very simply into a problem of intersection theory. It's basically Z to the B4 modulo this intersection matrix of compact 4 cycles of divisors with compact curves times Z to the B2. So this is just calculating this quotient, and this here we can compute from the resolution. But what's actually nice, even more conceptually interesting perhaps, is that this quotient here, you could also, using this long exact sequence in Rasp homology, map to a statement that is gamma 1 is essentially sitting inside, or very often, if you don't have any suitable one cycles in the bulk, is actually H1 of the boundary. So in fact, for all purposes in this talk, the one form symmetry is actually given by calculating the H1 homology of the link. Right, so we have a canonical singularity, it's a threefold. The link is a 5 manifold. We can calculate the first homology of that. So that's, as Matt said, for physicists, it's useful to look at an example. I think mathematicians also like examples. So let's look at an example. So one class is X is toric, and the boundary is one of these Sasaki-Einstein YPQ spaces. The cone over that is a canonical singularity. It's a canonical singularity with the link is YPQ. So this is a circle bundle with C1, P, and Q over P1 times P1. And for this, it's known by results by Boyer et al. That this actually H1 is GCD PQ. And in fact, the physics, by looking at the Coulomb branch and looking at what kind of non-abelian enhancements we have, actually this is the canonical singularity for the SUP gauge theory with the Chern-Simons level Q. And that indeed has a ZPQ one form symmetry, because you have the center symmetry, ZP, but then you have the Q, Chern-Simons level says there's a charge Q instant on particle, and that screens the one form symmetry to the GCD of P and Q. We can also do this from the intersection calculation, but actually the beauty of this is you don't really need to have any kind of gauge theoretic description of these theories. Right? This is a purely now geometric statement, and so we can also calculate this for theories that are non-Lagrangian, in the sense of there's no locus on the Coulomb branch, but there's some non-abelian gauge theory. And this, the first example is this famous P2 Seiberg theory, which is essentially sitting in this class of theories by furthermore doing decoupling matter. So you decouple from the SU2 zero theory, the instanton particle, you get to this theory here. And in fact, you get for this P2, there's also one form symmetry, which is Z3. Okay, so now how do we calculate now the two group? So we've got a one form symmetry, we've got a zero form symmetry. When do I actually see the two group symmetry? So for this, we now need to actually also look at the charges of local operators under the flavor symmetry. So in fact, in this intersection way of looking at it, I'll just briefly discuss this, because I want to actually go to the link discussion. We now look at both this matrix M42, which entered into the computation of the one form symmetry, but also now the intersection between compact, non-compact divisors and the curve. So that's basically the flavor charges of the local operators. Oh wow, the weather has changed. So this actually, what we showed in this paper here is that this quotient here now calculates what this extension group E was. And again, it's purely, you do your algebraic geometry and it falls out of that calculation, and E is basically this quotient here. And then from this, we can compute the two groups. So let's look at again as an example. So the simplest theory that sort of has a gauge theory description is the SU2 pure gauge theory, no Chern-Simons level. Here the compact, it's rank one. There's one, when we resolve this, there's one compact divisor, which is a Hirzebruch 2 surface. So it's P1 5 over P1. And torically, I can realize this in terms of this toric diagram. So these are the toric, so it's actually a three-dimensional thing, but because it's a Calabi-Yau, they only lie in a two-plane, these vertices. So in fact, I'm just looking at this two-dimensional sublattice. And so these three external vertices plus this one internal vertex in the toric diagram are the divisors. This is the compact divisors. And these are non-compact, but are relations with actually only one non-compact divisor, D. So when I resolve this, I triangulate the toric diagram. And in fact, there are these curves, the E and the F curves. We can calculate the intersections of this. And in fact, this tells us, that Okay, now look at the Smith decomposition of this matrix of intersections. There's a 4, 1. So in fact, this group E is a Z4 group. The one form symmetry we can calculate equally. So in fact, that's sort of done by just looking at the external vertices in this case, and that's actually a Z2. So in fact, in this case, this extension is Z2 one form symmetry to Z4 to Z2. And this is a non-trivial extension. And in fact, the flavor symmetry group is now actually an SO3. So this is precisely this example here. And that global formative flavor can also be checked, for example, using the superconformal index or some anomalies. Okay, so now let's just go briefly through how this two group really is now comes to life. Now we see the background for the one form symmetry be determined by the zero form symmetry background. So we have an SO3 flavor symmetry group. There is no kind of obstruction W2 to lifting these SO3 bundles to SU2 ones. And essentially, this W2 class now will participate in this Bochstein homomorphism. If I apply the Bochstein to this Bochstein of W2, will give us a non-trivial result, and that's the variation for the background of the one form symmetry. So that's a two group symmetry in this theory here. So this theory has a two group symmetry. Okay, so that's sort of the bulk picture of two groups. I calculate intersections, and from there I can infer this non-trivial relation between the zero and the one form symmetries. That's nice, but actually there's a much more intuitive way, right? So we were thinking at the beginning in terms of lines, local operators, lines, and different relations, equivalence relations. And that's actually what we can now formulate also in terms of this link, the boundary of the space. And so I want to discuss this now a bit more. So we already saw that the link is this Sasaki-Einstein type 5 manifolds. So let's just call it L5. And one important caveat here is I have to geometrically realize the flavor symmetry algebra. The non-abelian algebra needs to be manifest in the geometry. So for the experts, I can't apply this in the case of this SU2 zero theory for the F0, because there the flavor symmetry is not manifest. That's the only caveat here. Okay, so now if I have this 5-dimensional link, and I have these non-compact divisors, I can ask this, these are basically what they yield at the boundary, they're singularities. And let's call this space S0, the singularity coming from this flavor symmetry intersected with the link. So what I want to now actually see is both the one form symmetry and the two group from just this kind of picture of lines screened by local operators. So we said the one form symmetry comes from H2 of X del X, modulo screening. And by going back, oops, I'm not going back in the wrong direction. So this here, that in fact the one form symmetry you could really think of as H1 of the boundary. So if I now think of basically line operators, Pontryagin duo of the one form symmetry line operators is one cycles. So gamma 1 in this picture is basically a one cycle on the boundary. LD is the link L5 for us. And now there's another one, gamma 2. And I'm asking, are these two equivalent line operators, right? So this was basically the statement here is gamma 1, gamma 2 on the boundary. These are one cycles. Are they equivalent? So the answer is, well, if there is actually a two chain C12, this yellow thing, whose boundary is gamma 1, gamma 2, then in fact, when I wrap an M2 brane on this yellow chain, I get a local operator. And in fact, that will have exactly the property that it will link between these two things. So Matt, this is basically the picture that you were asking about on the boundary. So this is just seeing that one form symmetry in terms of a geometric construction on the boundary. So now the more tricky thing is, how do we see this relation gamma twiddle prime? So we actually now don't want to include line changing operators that are charged on the center of the flavor symmetry. So in fact, for this, I'll excise a bit around the singularity here. Let's close to a little neighborhood around S0, S, and I'll excise this from this link. And then I actually have a chain that passes through this, right? If this yellow chain, now if I actually cut out this piece here, right, this acquires another boundary component, then in fact, these two gamma 1, gamma 2s may not be actually equivalent anymore. They're not screened in the same way. So in fact, the only relevant ones that are not charged under the C are the ones that are in H1 of the link with the singularity or local neighborhood of the singularity excised. And that's actually the group we had. So to see that actually the ones that that this really excludes these guys that are charged on the C, you can also look at the following picture. So they have a trivial line. So gamma here is a trivial line. So this is something that would not be a non-trivial. So from a gauge theory point of view, it's not in one form symmetry. But if I actually now excise this, if I look at this as 0, and now in fact, if this gamma actually is in a one cycle on the boundary of S, then in fact this is sort of something that's charged and effectively the center of the flavor symmetry, right? So if I take gamma to be now actually in the torsion part of the H1 of the boundary, then that actually says, just like in the argument how we derived one form symmetry for the bulk theory, this is actually now the center of the flavor symmetry. And so that's precisely what we call C. So what appears here on the left is C, in the middle is E, and H1 of the link was the one form symmetry. So this is how on the link, this extension sequence is now computed in terms of the boundary homology. So the idea is you need to calculate now the homology for the link with the singularity excised. And again, we can do this in a toric example. So what is my time? That's very good. So applied to these toric models, there's an extremely nice computational way of calculating the homology groups for the link, which was developed in this paper by Nameki and Ben Heidenreich. So the link actually can be modeled by sort of a 3-chain of length spaces that are glued along torsion 1 cycles. So in fact, I think the best way to sort of see this is to actually do an example. But essentially, the point is this H1 of B is computed very simply from a combinatorial formula in terms of the data on the vertices of the toric diagram. So in fact, these NIs are just the volumes of triangles of consecutive vertices in the toric diagram. And so you take the GCD of all of these NIs. And likewise, now the E hat is computed in the same way, but now excising some components of this boundary. So the way you should think about this is as follows. So for the SU2, essentially this was the toric diagram. And now these asymptotic length spaces that appear, you can think of these as glued together at the boundary along the torsion 1 cycles. And in fact, if there's an internal vertex, it's just an S2 times an S1. So in this case here, this is just this S3 mod, for example, Z4 is coming from this computing the volume between these consecutive vertices here. So this is a Z4. For example, this one here is a Z2 because you're calculating the volume of of this vertex, and that vertex, and so on. So you get an S3 mod Z2, and so the GCD of these Z2. So that's just the one form symmetry for the SU2 theory. Now the interesting thing is when we excise the flavor symmetry node, so this is where the singularity sits. So locally, this edge here has an A1 singularity. Then actually you lose those two S3 mod Z2s, become contractible, and all that you're left with is the S3 mod Z4. And so in fact you get that we had here is Z4, and that's precisely confirming what we said before. In this case, we have a Z2 center of the flavor symmetry and the extension Z2, Z4, Z2. So that's just sort of rephrasing what the computation we did before. But now we can generalize it to any kind of SUN level N, right? So we calculate these different kind of asymptotic length spaces and excised ones. And then, for example, in this case for SUN level N, when this n is even, then there's a non-trivial extension sequence like that, and there's a tuple. So all of this doesn't depend on there being a gauge theory description. You can do this also for non-Lagrangian theories. And for example, this is sort of a generalization of this P2 theory. This does not have a gauge theory description, this toric diagram, but nevertheless, we can compute now the one form symmetry and the two group symmetry for this. So right, we start with this asymptotic, on the left-hand side is just a toric diagram. From there, we can see this has actually a one form symmetry, which is Z4. Once we excise the flavor node, the SU2 flavor node on this edge, and then compute the asymptotics with S3 mod Z8. So this has actually the extension group Z8 here. So then again, there's a tuple. There's a question, yes?
The fact that
That's right, yes. Because indeed, on the Coulomb branch, you lose the non-abelian. So in fact, that's something you can see already for the SU2, right? So on the Coulomb branch, you basically resolve the full thing, and then, okay, so here's, I think it's a little bit more subtle than that, because what you really need to is not just that there's some extension. What you also need to know is that there's a non-trivial obstruction. So in the case of, for example, the SU2 on the Coulomb branch, you actually have, keep using the pen. So SU2, so what Cyril is asking, if you take SU2 and you go to the Coulomb branch, or it's some U1 gauge theory, the flavor here was SO3, but here the flavor symmetry is SU2 mod Z2. Now, in fact, here the obstruction to lifting is this W2 and VSO3. But here it would be so in fact, this class is trivial. So in the Coulomb branch, you don't have a tuple. So this is, however, has to do with the fact that this obstruction class vanishes, right? It's not so much to do with this extension group, but actually that this obstruction class, this flavor symmetry thing is not there. No, this is really Coulomb branch. So okay, so I'm also talking about, I really go to the full Coulomb branch. Yeah. But that doesn't matter, right? Because flavor symmetry, once you go away from the SCFT point, you will break it to U1 because you have no flavor, so there's just U1 topological, right? So that happens also for the SU2 gauge theory. Yeah. That's right. You resolve the A1 singularity, and all this S3 mod Z2 goes away. Exactly. Yeah. Perfect. I'm transmitting information. Okay. So the point I was making in this example is, right, so far, this SU2 examples, so they're all Lagrangian of the Coulomb, but this one here doesn't have any kind of sensible gauge description, but nevertheless, you can still now detect whether it has these symmetries. And what's also particularly nice about this boundary perspective is you don't need to know, you don't need to rely on a resolution or a deformation to gain information about the theory, right? So this seems to be very much information about the CFT rather than the theory studied on the Coulomb branch or inferred from the Coulomb branch. So there's some way also to think about this from the dual brainwave perspective. So I can either talk about this in the next 3 minutes. Yeah, maybe we do this because I think there's a nice geometry question, and then people can ask me about non-invertibles later. Okay, so in physics, there is a duality of this M theory setup. So some string theory duality. And then you can think of, you take this dual picture to this toric diagram. And so if you're a topical geometry person, you'll recognize that this could be a sort of topical geometry, and there's some truth to that. So anyway, these brainwaves, the dual 5 brainwaves, are type 2B description of the same gauge series. So this SU2 theory that I drew here basically has a dual brainwave description. So the way you should think about it is that these lines are 5 brains, and they have particular makings, and they can have PQ charge, they can be D5, NS5, or mixtures thereof, and each sort of edge on the toric diagram will tell you about the charges of these 5 brains in this way. And so there's a precise algorithm how to get from one to the other. And so now we can use this to generalize the story beyond geometric, so toric models. So whenever you have parallel 5 branes, so in this case, there were parallel 5 branes. That basically is always the case when you have an edge with some non-isolated singularity, right? So there's a vertex along the edge here. So this is the SU2 flavor symmetry node. Whenever you have 2 parallel 5 branes or multiple 5 branes, you actually get a flavor symmetry. And so now we can repeat the whole analysis, calculate the symmetries. In fact, from the toric, from this dual web diagram, the one form symmetry is just basically calculating the Smith decomposition of the charge matrix of the P and Q charges. And then actually the extension group E that sort of determines the 2-group symmetry is just obtained by now reducing this. So we were saying before in the toric geometry, we excise the singularity. So here you remove the toric, the parallel 5 branes from your charge matrix. That's literally a translation of the problem. So this reduced charge matrix is just removing these PQ guys that are basically with multiplicity bigger than 1. In this case, you'd just be removing these 2. Okay, but why is that interesting? Because, well, toric Calabi-Yaos only cover a limited subset of 5-dimensional SCFTs. So these other geometric methods I was discussing, resolving canonical singularities, is much broader. But if you're in toric models, you're somewhat limited. But there's a generalization that sort of physicists have proposed of toric geometry, which essentially says, well, these 5 branes, they don't need to, if you have parallel 5 branes, they don't actually need to sort of all go to infinity. It can actually end on 7 branes. And so in the toric diagram, that's modeled by just saying along this edge, where we had 2 5 branes that were parallel, right? Actually, those 2 are now ending on a single 7 brane. It should correspond to something like a deformation of the geometry. But there's sort of a very precise brane configuration that models this. And this diagram, so where this white dot just meant the 2 parallel 5 branes are just fused and end on a single 7 brane. And this theory, this diagram of the dual web describes, for example, this gauge theory. And this gauge theory has one form symmetry because the center is broken to Z2. So it has a Z2 center symmetry. And now you could ask, can I generalize what I was doing to this set? I don't really know what it means in the toric language because it's something that has to be still developed. But in fact, we can see, in fact, applying now this sort of link boundary topology picture here also gives the correct one form symmetry in 2 group. So for example, here we can define now there's an associated GTP. So these guys are called generalized toric polygons. This terminology was from our paper, but they were first sort of proposed in this, I think, paper by Benini, Benvenuti, Tachikawa. So GTPs are generalized toric polygons with these white dots. So these actually give multiplicities to these edges, right? So you have here this 2, 2 rather than 1, 1, which we would have in the standard toric diagram. You can apply basically to the diagram with the black dot with an actual vertex put back in and calculate what I was calculating so far, and you get the correct thing. So there's some truth to these GTPs that I think would be very nice to work out mathematically what kind of geometries they are. And certainly the link topology seems to work very similar to the case of standard torics. Okay, so some comments about this. Right, so what I discussed was in the context of canonical singularities, for example, torics, but also more generally. But really, most of these structures, one-form symmetries, labor symmetries, higher group structures, they didn't really depend on this being a Calabi-Yau. You could do this equally for other dimensional Calabi-Yaus or for G2 manifolds, anything that had preserved supersymmetries with some kind of reduced holonomy compactification. And in fact, in a couple last 2 weeks, there were various papers generalizing some of these aspects in various ways. Another point that sort of I was trying to emphasize is looking at the boundary of these singularities is very, very insightful. In fact, sort of there's this philosophy that I think Dan Fried proposed to think of these kind of symmetry TFTs. So they're like anomaly theories. They capture the topological theories often. They capture the anomalies of a given quantum field theory. And basically we can compute that from the reduction on the link. So for example, you can calculate the one-form symmetries. You can calculate anomalies from this sort of construction. So for example, in these 5-dimensional theories, these SUP level Q theories, reducing on these links YPQ, we find these types of anomalies between the one-form symmetry on its own, but also the instantaneous one symmetry and the one-form symmetry. In that context, we should also be able to then see an imprint of these 2 groups much more directly. So a 2 group was this kind of gadget where you had delta B2 as some Posnikov class theta, say in our case this was this Bockstein W2. Now, when you gauge the one-form symmetry, if you can gauge the one-form symmetry, this is actually equivalent that this maps to a theory where the one-form symmetry maps to a 2-form symmetry. In 5D, the dual is a 2-form symmetry. So you should then find a coupling in this anomaly theory in the SymTFT B3 Bock W2. And so that actually would be another imprint of this 2 group on the from the boundary and this anomaly theory. Okay, so now there's a whole new chapter, and I'll spare you that. And but actually, that's I think the most exciting part. Anyway, we'll leave you with a couple of questions. We discussed a lot of these symmetries, and if you have encountered one-form symmetries before, in 4 dimensions, there's really interesting physics associated to them. They basically tell us whether a particular vacuum is confining or not, something physicists care a lot about. What actually is the role of these higher form symmetries, the physics of that in higher dimensions or in CFTs in general? And what is the physics of these 2 group symmetries? And then I think the most interesting question is really to have a more systematic sort of universal framework to compute these or derive these from M theory on these boundary geometries. Okay, so thanks very much, and sorry for overrunning by 6 minutes. Okay. Yeah, Matt? So the question Matt is asking is, very early on, here. So if we actually look at the case when these AIs are non-zero, so in fact, let's say we have a canonical singularity and you can't do any big resolution. It's stuck. You can do a bunch of small resolution. So you have AIs are non-zero. What is this issue? The one thing that can be, these things can have some. It would be interesting to say, well, perhaps this comes from creating Form Symmetries. It's not something that I think to full satisfaction has been shown that any such theory is actually just I think very allowed is to have these are distinct. It's a similar question.
Yeah, I mean,
so there were papers trying to connect these two oceans to and this is not something. No. I'm just getting mad.
Yeah, I have so many anomalies.
Yeah.
Think about it.
Yeah, you can have anomaly.
There might be a single structure.
Yeah, so for example, for PQ, thing. And they can have anomalies.
In those cases, I would have thought that
Yes, it's a good point.
B2 is not closed.
Yes, you're saying there should be now additional two-group anomaly.
And then further terms, we see that it's symmetry.
Very interesting. So what he's asking is if you have an anomaly like that, and delta B2 is enclosed, and it's not automatic the delta of the anomaly. Right? And so we need to be more careful of actually because there should be some what's called a two-group anomaly, and they're actually compatible with this non-closure of B2. And that's an interesting question to say.